Welcome to UC Science Radio, where we conduct interviews with a range of scientists to learn about the big issues facing our world and what science is doing to help. I'm Molly McGidd, a master's student in the School of Biological Sciences. Today, I'm talking with Dr. Michele Bannister. She's a planetary astronomer, poet, and hunter of new and strange worlds. She's been involved in the discovery of more than 800 minor planets, and even has an asteroid named after her. She's interested in understanding how planets formed, evolved, and reached their present orbits. Kia ora, Michele. Welcome to UC Science Radio. I'm interested in your role at UC, so what do you do and what's your research about?
Morena, and thank you for having me on. So I'm a planetary astronomer in Te Kuramatu, the School of Physical and Chemical Sciences. So I study the formation and evolution of our solar system, how it comes to be in a disk of swirling gas and dust, how it forms and evolves once the planets are formed, and the little worlds of the solar system left over from that formation are moved onto the orbits where we see them today. And I try and map out what exists in the outermost reaches of the solar system.
What are those little worlds?
You might think of them as like the little cousins of Pluto. Pluto's far now. The small, maybe the size of an island, maybe the size of, the North Island or Te Ika a Maui, all the way up to the size of Australia. These are worlds that are left over from the formation of the solar system. We think these worlds are effectively unchanged when they orbit in the outermost parts of the solar system through to what we see today. So ones like comets, for instance, they don't get heated by the sun very much until they come in close to the sun and start to sublime and you see a tail coming off. But the ones that orbit out beyond Neptune, some of those, the ones on round, flat orbits, they've never actually gone anywhere. So they're effectively primordial.
Wow, so they've been there since the beginning of the universe.
Since the solar system formed, yeah.
Since the solar system formed. Wow, that's incredible. And I know some of your work recently I've seen in the news has been looking at an interstellar object that came into the solar system.
Yeah, so interstellar objects are a really exciting new field of study. So in exactly the same way as our solar system formed trillions on trillions of these little icy planetesimals and little rocky planetesimals closer into the star in the early days of the solar system, planetary systems all across the galaxy did the same thing. And one of the things that happens in the evolution of a planetary system is that the planets in it migrate. And by migrate, they move from where they form to somewhere else in the disk, often closer into the star. And that movement, that migration, throws out trillions on trillions of the little worlds. So we end up with maybe a tiny fraction, 1 to 5% of the ones that were originally formed in the disk. And the rest of them, 95%, they just go off and wander the galaxy. And so, stars all across the galaxy do this. And so we have this background of interstellar objects. So it had been predicted for decades that there were going to be interstellar objects would one day be seen. And in 2017, we had the first one that was seen called Interstellar 1, One-Eye Oumuamua. So Oumuamua was named because it was found by a Hawaiian telescope. And it means the first messenger arriving from afar. And the second one was found by an astronomer, Gennady Borisov, in the Crimean Astronomical Observatory is where he works. So he's an amateur and found it with a telescope he made himself. And so that one's named after him. So it's named Twoeyes Borisov.
And how do you know that it's an interstellar object as compared to just something floating around from our own solar system?
The path that they take through the solar system. Everything that's in the solar system is bound to the sun. It orbits the sun. So the shape of that orbit is a circle or a more distorted circle in ellipse, all the way out to a parabola. But if there's something that's unbound to the sun, then the shape of that orbit, the eccentricity of it, it goes greater than 1, and it's unbound from the sun. And so both One-Eye and Twoeyes have had these hyperbolic orbits, these ones where they're clearly unbound from the sun. And they're also traveling very fast. So they travel at a velocity relative to infinity, which is substantially greater than anything that could be just from the Oort cloud, from the comet cloud at the edge of our solar system. So that's the two distinguishing features. We look for their velocity and we look for the shape of their trajectory.
Is Twoeyes still in our solar system? Can you still see it?
Yeah. Well, both of them are still in our solar system. Our solar system's big. They might be going really fast, but it still takes a long while to go by. Yeah, so Twoeye we can still observe. And so I've been part of a team that started observing in late October last year. And we were observing all the way through February and into early March here. And we've been able to get some really interesting observations of it so far. This one's really fun because the first one, it didn't act like a comet in the sense of it didn't have a big flashy tail like a streamer behind it. We could just see it as a point source, kind of like an asteroid, right? And the advantage of that is you can see the surface directly. So there's no obscuring cloud of material around it. So we could see the surface directly, so that was good. But for this one, it does have that big flashy cloud of subliming material coming off it. And that's the ices of it subliming. So this is probably, as far as we can tell, the first time that this little icy world has been heated ever since it formed in its birth disk somewhere at another star across the galaxy. It's letting off a remarkable amount of different sorts of ices. So ices of things like cyanogen, which is a bit related to cyanide, which is a really common molecule you see in comets in our system. But it's also letting off a really large amount of carbon monoxide, substantially more than almost any other comet that we've ever seen in our own system. You know, this direct sample of the chemistry of the disk that formed planets around another star. You can't do that with any other sort of astronomy. It's like a piece of another star that's just come right here so we can measure it. And it turns out to be different.
And you talked sort of describing things as planetesimals. What makes something an actual planet? Like, when does it get that distinction versus a planetesimal?
So for me, it's mass. Something that's big enough to pull itself into being round, which happens at about a diameter of 400 kilometers or so. That's when we start thinking of things, by we I mean kind of planetary scientists, often start looking at the physical processes that take place inside a world like that. They start to be a bit different. So when something's big enough to pull all its material into being a round world, then you can start to have quite different geology happening in its interior. You start to get the formation of a core and a mantle and a crust, and that can start to evolve. And that happens around 400 kilometers. Something smaller than that, I'd still call something at 400 kilometers a planetesimal necessarily, but then between about 400 and about 2000, you start getting into dwarf planet scale. And something really massive, like when something gets up to being, Earth mass or Venus mass, which is basically the same mass, like then it's a proper sized planet.
And how do planets form? I don't know.
I wish we did. Right? So this is actually one of the really big questions that we have in astronomy, I would say, is just how do we actually get from a disk of gas in a mixture with very fine dust? So by very fine, I mean anything from the size of grains of sand, like at the millimeter scale, all the way down to the micron scale. So this is, even finer than the dust you find in your dust bunnies under the sofa. You start with a molecular cloud of gas and dust, and that's a very, very tenuous thing. They occupy huge volumes, often tens and tens of light years. And you get denser regions within these, clumps and cores, and those start to infall under the gravitational force. And then, boom, you get enough density that you start to have a star and a forming disk of material around that. And conservation of angular momentum means that what started as a roundish or filamentary cloud structure collapses into a flattened spinning disk. So once you have this flattened spinning disk of gas and dust with a forming star in the center of it, then you need to go from dust all the way up to things that are planet-sized. And, that's a huge difference in both size scale. It's several orders of magnitude, and it's a huge difference in mass scale. Like in some cases, it can be as much as 30 orders of magnitude in mass. And that's physically really hard to do. And it's one of the things, there's a number of key physical mechanisms of like how the gas and dust react with each other, things called the streaming instability, which allow planetesimals to kind of go cloop and simultaneously just all collapse out of the disk in a way that predominantly makes pairs of planetesimals, little binaries. And that kind of matches what we're starting to observe in the Kuiper belt out beyond Neptune, these primordial ones I was mentioning earlier. And for larger situations, once you start getting up kind of above that 400 or so kilometre scale, past masses of, like the mass of the largest asteroid we see in the asteroid belt, for instance, like asteroid Ceres, then you start getting things like pebble accretion, where the gravitational force of the forming planetary core focuses the pebbles down onto it. And the whole key for making a planet is to get a situation called runaway growth, where the biggest thing can start to suck in mass most quickly and then accrete an envelope of gas. And that's when you end up with your Jupiters, your Saturns, your gas giant planets, and they dominate quite quickly. But you have to do this fast because the gas all goes away as the star turns on and the winds of the star rip through the disk and blow out the last of the gas. You have to do that within about, at most, 1 to 3 million years. So planets have to form really quickly.
What is the most fun or exciting part of your research?
That's hard. The thing that comes to mind is one of the things I was doing a lot with us is with the Outer Solar System Origin Survey, which is we discovered over 800 new trans-Neptunian objects, these little planetesimals out beyond Neptune, as part of that survey. And so I'd be looking through the images and we would have entirely new worlds that no one had ever identified before in these images. So I'd be looking at this little dot of light, this little unresolved point of light, and linking up its orbit across these other images that we'd acquired to be able to go, hey, this is where it orbits. It's out beyond Neptune. I can tell the shape of its orbit from these measurements. Look, I'll keep adding more measurements. Oh, now I can see where it lives. From where it lives, I can tell a little bit about its history. And every time I would go, wow, no one's seen this world before. I am literally the first person to know that this exists. And now I can tell other people about it. This is so much fun. So yeah, that little wonder that the universe has got so many things in it that are new and incredible to see, and being able to share that with other people.
What's next for you? What's the next thing that you're excited about?
I'm really keen on a project at the moment where we're looking at what implications there can be for this background population of interstellar objects wandering between the stars. So as stars form these planetesimals and throw them out to wander the space between the stars all across the galaxy, you get this background of wandering interstellar objects. And as new generations of stars form and make more planetesimals, that background's going to build up, become a little more denser over time. And in the present day, the detection of the interstellar object from calibrated surveys that we do have suggests that there's a really high density of these, that it's about 10 to the 15 per cubic parsec, which, if I put that in context, basically means inside the orbit of Mars in our system, there's an interstellar object right now, something that's 100 meters in size, the size of a skyscraper or such, or a little larger. So yeah, there's a lot of these things. And so they have to be traveling through molecular clouds, which are the places that planetary systems all start. And they have to get swept up when the molecular clouds collapse inward. So planetary systems in the current epoch of the galaxy have to be seeded, at least studded, with the interstellar objects that came from previous generations of planetary systems. And so what I'm looking at is how significant is that process. So I have a paper with Suzanne Valsner where we co-proposed this idea that suggests you'd get between 1 million and 10 million of these objects in each new planetary system. So when you put that on something where all the rest of the material is, size of sand grains through to dust grains, how does that affect how the process of planetesimal formation takes place? It's a really fun playground of an idea. How does it change over the course of the galaxy? Does it mean that planet formation in the first few billion years of the galaxy happened slightly differently from how it does now? How does it happen if you merge two galaxies together and now you get the interstellar objects from one galaxy and the interstellar objects from, say, the Milky Way, and you merge those together and now you have a background population from two different galaxies? So yeah, now we have intergalactic interstellar objects to think about. So it's fun. It's a idea where you have the smallest worlds that a planetary system can make, and then you end up having to think about them on the scale of galaxies. And that's not something I'm used to doing. I'm a person who likes to hit things with a hammer on occasion. I started as a geologist. So, yeah, there's one of these transformations in how you think about the world that has been really fun working on this over the last year or so. And so I'm definitely looking forward to doing more with that over the future.
How do you think learning about things out in space can affect our lives or how we think about ourselves?
A lot of different ways. So I'm focused on trying to tell the history of our home, of our place in the universe. How did our solar system, our little planetary system, how did that come to be? And putting that in context with the larger story of why do we have planets? Why do stars have planets? How do they get planets? Is our home in the galaxy unique in some way? Is it a regular sort of planetary system? That's the larger questions that I tend to work with. But on a much more field specific level, I work with small bodies all across the solar system. I also work on asteroids, and asteroids affect life on Earth in very many different ways. The biggest impact that we have led to the formation of our moon, which is an incredibly important aspect of so many different facets of our lives, from culture to tides to everything else about the biosphere, to stabilizing our planet so that our spin axis is nice and steady and we have a nice regular climate. Impacts are a thing that sculpt our planet and our biosphere all through cosmic time. And even today, we still have to be conscious of things like impact threat, of mapping out how near-Earth asteroids can potentially hit the Earth and making sure that we know where all of them are, and mapping them with sky surveys is one of the aspects of what I do, to make sure we know that there aren't any that could ever hit us. And so making sure that the Earth is completely safe for that is definitely one aspect of my job as well. And also, when people understand how planets work, understand how our Earth can have a biosphere, and yet Venus, which is the same mass as us but orbits in just a little closer, is this incredibly high temperature world with sulfuric acid clouds and completely hostile to life, how we can have a planetary twin in our system that's like ours but so different. This taps into how people understand how our little biosphere is precious. We don't know of any other instances of life anywhere in our solar system or anywhere else across the galaxy, despite all the potentially habitable environments we have in the solar system, all the ocean worlds like Europa and Enceladus, where you have liquid water oceans under thick ice shells. Our place is precious, and this is something planetary science can make us very aware of, and how much work we have to do to keep our little home in this very, very big and entirely empty cosmos.
So, something else that you do is you're a poet. I've seen some of your poetry. It seems like it takes themes, at least, and ideas from your work. So, what's it like to write in this more creative way about your research and things that you're thinking about? And how does that differ from writing, for grants or writing for scientific papers? How do those different styles of writing either complement each other or allow you to explore these ideas in different ways?
It's one of those things that it's always been really important to me. And I think it's one of those ways in which people sometimes go, oh, creative writing and science are two different things. And I'm like, no, it's absolutely key to be able to have both of those. And yeah, so I think being able to write poetry and write creatively is absolutely key to what makes me any good as a scientist. I remember like one of the sets of comments on my PhD did mention that there was a bit too much like flowery language in some parts of my PhD, which I take that as a badge of honor these days. But it's one of those things where being able to think about some of these very interesting ideas, how do planets form and evolve, what makes particular sorts of planets interesting, how do gas giants differ from tiny little rocky worlds, what does it mean when you have an ice shell over a thick ocean. I find poetry a very useful way for trying to change and develop some of my ideas for this. And this is why, I definitely try and do as much as I can for writing for the general public, because it allows you to craft better sentences. And sure, that ties back into your scientific writing as well. You learn different modes of writing. Of course, scientific writing for a journal, you're trying to present a very clear argument and a very clear set of descriptions of the techniques and methods you work through. But you're also trying to convey information. And in poetry, you have to do that in a very succinct way quite often. You're trying to make a very condensed argument with a lot of emotion and nuance. And in scientific writing, you're trying to make a condensed argument with sophistication and nuance. So they feed back and forth. And I think also reading poetry is really good for trying to improve the language, learning how other people can make beautiful sentences that are so nuanced. And that's something that it always feeds back and forward. So between poetry and public writing and scientific writing, you get a lot better at each by doing one of the other.
Yeah, and I think there's this idea that scientists should keep to themselves and be in their own communities, but I think that's harmful because it's limiting yourself to the perspectives of people who've had the same experiences, same background, same education generally, and it prevents bigger, more widespread ideas from happening and from that interdisciplinary exchange.
Yeah, and I think in terms of communities, there's a surprisingly more overlap between the communities of people who primarily come into poetry from the literature side of things, or literature, folklore, creative writing, and the more traditionally just physical sciences path. There's more overlap between those communities than you'd think, but I do appreciate a lot. One of the things that working in both poetry and physical sciences means that I do encounter people a lot who don't think about physical sciences on a day-to-day basis, and how they view the world is that, that's wonderfully refreshing. It's one of those things where I'm like, oh, I should have thought about that way. That's really helpful. And, maybe they encounter my frame of mind, which is a little more physical sciences based, and I can point something out that we do know about the universe, and then they go off and make some work of art that sparks and picks up from that, and that's really exciting to see as well.
My last question is, in one sentence, could you say why your work is so important?
Because it's a big universe. We're never going to know everything about it, but we can find out a little bit more about each corner of it as we go.
Thanks, Michele. I really enjoyed talking with you.